Alright class, so last time we finished talking about intermolecular forces and we did a couple practice problems. Now we say that intermolecular forces matter because they determine physical property, right? So we're going to go over some of these physical properties today. The first physical property we're going to talk about viscosity. Viscosity. Now, what is viscosity? What viscosity is basically a measure of a fluid's resistance to flow. Now, to basically simplify it, basically is the thickness of a liquid. Have you ever noticed that people who are wine drinkers, the minute they get their wine, they swirl it around, they shake their wine around, and I do it too, but I just wanted to be cool and I had no idea what it actually means. But I've learned recently they're looking for the viscosity of the wine when they're shaking their wine around. Now, and we're going to talk about that, how to figure out the viscosity of the wine and what that means in a second. Now let's go back to IMF. If you have a higher intermolecular forces, do you think you're going to have a higher viscosity or lower viscosity? If you have a higher intermolecular forces, that means you have a lot of attraction, right? That means that all of these molecules are really attracted together, so the viscosity will also be higher. The viscosity will also be higher. Okay. Now, if you raise the temperature, if you heat something up, what happens to the viscosity? The viscosity goes down, and you already know that when you heat up the liquid, they become less thick, right? Okay, so far so good. Now, I want to put a structure on the board for you. This is the structure of glycerol. Glycerol is basically, you can find it in lotion. So next time you're using lotion, think about this. Okay. Now, here's a question. This is glycerol. Do you think glycerol would have a high viscosity or low viscosity? Do you think glycerol has a high or low viscosity? Think about it. I know you have a 50-50 chance. It has a high viscosity. But here's why. When you look at the glycerol, what kind of IMF are you looking for? Ooh, look at this. Those are OH. What is that? Hydrogen bonding. It has 3 sites for hydrogen bonding. If you have 3 sites for hydrogen bonding, you are going to have a high intermolecular forces because you have 3 sites for hydrogen bonding. Okay, so higher IMF, that means a higher viscosity. Now let's go back to wine. So the wine drinkers, they take their wine, they swirl it around. What are they looking for? Now, alcohol, wine, any kind of alcohol, they are made of OH. OH is basically alcohol. So if you have a lot of alcohol in your wine, if your wine has a high concentration of alcohol, what happens to the viscosity? It's going to be more viscous. And that's what they're looking for. It's kind of cool. So once you guys are 21, and if you ever have wine, try that out. And then think about viscosity and think about the chemistry class that you took. Alright, so that was viscosity. The next one we're going to go over is surface tension. And a lot of these things you already know. So it's surface tension. What is surface tension? What surface tension is a measure of the elastic force. At the surface of a liquid. I don't like defining things, but some people do, so I'm putting this out for you guys. Now, okay, in the morning, when you go to your car, and right now you guys are not, But before this whole drama happened and we were coming to school, when you went to your car in the morning, you saw water droplets on your car, didn't you? Yeah. Actually, try it even now. Tomorrow morning, go to your car and then see if you see water droplets in your car. If you look at those water droplets, so if you go to your car, what you're gonna have? You're gonna have all these water droplets on your car, and they beat up. So you're gonna round looking water droplets on your car surface. Okay. Now, if I have a surface, if I have a glass surface, and if I add a drop of water, it will not be this nice round beat up shape. What is going to look like is going to spread out. This is what my water is going to look like. It's going to spread out. Now what's going on here? Here's what's going on. Water does not like your car surface, so it tries to get away from the car surface, and that's why it ends up being this nice droplet. Now if you add water to glass, water likes the glass surface, so it's actually going to spread out and tries to interact with the glass surface. Whereas here, it's not going to interact with the car surface. It's going to try to get away from the car surface. Likes the glass, is going to try to interact, and is going to spread out. So far, so good. Okay. Now, next thing. Capillary action. Capillary action. What's a capillary action? Is the ability of liquid to climb up a tube. So the liquid can climb up a tube, which is interesting because climbing up a tube, that's against gravity, isn't it? So let's talk about what is this capillary action. The liquid can climb up a tube and go against gravity. Now, capillary action is a combination of two things. It is a combination of cohesion forces and adhesion forces. Adhesion forces. So capillary action is a combination of cohesion and adhesion forces. Let's go over what's the cohesion force and what's the adhesion. Cohesion is attraction between liquid molecules. So cohesion is, give me 1 second, what is it? Is attraction between the liquid molecules when they're attracting with each other. What do you think adhesion is? Is attraction between liquid and the capillary wall. So it's an attraction, again I will give you an example to make more sense. Is attraction between the liquid and the capillary wall. So they're attracting with each other and also with a wall of whatever the tube is. Now, I want to make sure you really understand this. So let's draw a little picture. What I'm going to do, I'm going to draw a graduated cylinder. As you can see, my drawing hasn't really improved on an iPad either. Oh no. Okay. Alright. So, these are graduated cylinder. Just go with it. I know my drawings are not the best. Now, in this graduated cylinder, what I'm going to have H2O. Okay? In this one, I'm going to have mercury. Now, you already noticed when you put water in a graduated cylinder, you already noticed when you put water in a graduated cylinder, what does the water look like? Every time you put water in a graduated cylinder, the water has a meniscus, right? The water has a meniscus. Why does the water have a meniscus? So it has a concave shape. What does the water has a meniscus? Here's why. Because your graduate cylinder is glass, and glass is polar. Water is also polar. Water is polar, glass is polar. They like each other. So water is trying to actually interact with the glass surface, and that's why you get a little meniscus. Now, mercury is non-polar. So mercury is non-polar, but the glass is polar. So they don't really go with each other. It doesn't want to interact with the glass. It tries to get away from the glass, and that's why you have this little shape that is trying to get away from the glass. Whereas here, it tries to interact with the glass. That's why water has a meniscus. Okay. Now, there's one concept that I want you to remember, that especially when you go to organic chemistry. Here's what I want you to remember. Polar goes with polar. Non-polar goes with non-polar. You remember this for me? You're going to be in a really good shape. Polar goes with polar. Non-polar goes with non-polar. I need you to remember that. It's kind of like the same thing. You're going to go and hang out with people who are also taking chemistry class, right? Because you have something in common. You can interact. The same thing. Water is polar, glass is polar. They want to interact with each other. Okay. Now, next thing we're going to talk about is vapor pressure. Or we also call it VP, for vapor pressure. Okay. Now, I want to put up a little chart to explain exactly what vapor pressure is, to make sure you really understand this. Alright, so here the graph. Let me talk about vapor pressure. First of all, what is vaporization? Vaporization is when liquid turns into what? Turns into gas. Liquid turns into gas. That's vaporization, right? Okay. Now, check this out. Here we have a closed container, right? So we have all this liquid, let's say just water liquid. All the liquid molecules are right here. They have some IMF. They're hanging out together. Now, over time, some of it will get enough energy to go to the gas phase. So over time, some of them are going to get enough energy to go from liquid to gas phase. So far, so good? Okay. Now, gases moving around rapidly. We talked about that. As the gases are moving around rapidly, some of them are going to be hitting the walls of the container. When they're going to hit the contents of the container, they're going to go back to the solution. So then we have some of them, so some of them is going to go liquid to gas, but gases are moving around really rapidly at the room temperature. Some of them are going to hit the walls of the container. They're going to go back to the solution. So some of the gas will go back to the liquid. Now, at some point, you have the number of molecules that go from liquid to gas is going to equal the number of molecules that goes from gas to liquid. So at some point, the number of molecules that go gas to liquid and liquid to gas are going to equal. And at that point, it creates a pressure. And we're going to call that pressure a vapor pressure. Let me put up another picture to make sure you really understand this. So if you look at here, in this picture, I have 3 of the gas molecule, liquid molecule go to gas, and I have 3 of the gas molecule, they're going to hit the walls container and go back to the solution. So at some point, the number of gas to liquid, liquid to gas are going to equal to each other. That is going to create a pressure. This going up and down, this going back and forth between the gas and the liquid is going to create a pressure. We call that vapor pressure. So far, so good? Okay. Now, let's talk about this. If you have a high intermolecular forces Would you have a higher vapor pressure or lower vapor pressure? Now, before you answer that, I want you to think about this. If you have a high IMF, that means the molecules are going to be attracted together to each other, and they're going to hang on to each other pretty tightly. If they hang on to each other pretty tightly, they do not want to go to gas phase. So what do you think is going to happen to the vapor pressure? The vapor pressure is going to go down. So IMF goes up, the vapor pressure goes down. I'm going to explain it one more time. Because higher intermolecular forces, you have all this attraction. They are attracted to each other. These have a high IMF. That means these are attracted to each other, right? These are attracted to each other. So you have all these molecules that are really, really attracted to each other. They're holding on tightly. They're holding on tightly, and they have less tendency to go to the gas phase. So less of this is going to happen because they're hanging out, they're holding on tightly, so less likely to go up and less likely to go down. So because of that, you will have a lower vapor pressure. You would have a lower vapor pressure. So far, so good? Okay, nice job. Next one we're going to talk about boiling point. We're going to talk about boiling point. Okay, that's our last one. We're almost there. So we're going to talk about boiling point. We're going to talk about boiling point. And I do want to actually define boiling point because I think this is one of the definitions that is really good. Here's the definition of boiling point. Liquid boils when the vapor pressure matches the external pressure. When the vapor pressure matches the external pressure, the water or any kind of liquid will boil. Now, what is the boiling point of water? We always teach you that the boiling point of water is 100 degrees Celsius. But the boiling point of water is 100 degrees Celsius at 1 atm. As 1 atm. Alright, let me draw my mountain again. Alright, so here is at the sea level, we have 1 atm. And this is my sea level. Okay, so what do you think? At 1 atm, at the sea level, okay, the boiling point of water is 100 degrees. If you go higher up, you go hiking, you go higher up, and you want to boil water. What do you think? If you go high up, the boiling point of water is going to be higher than 100 or less than 100? What do you think? Now think about this. When you go higher, do you agree you have less gases, right? When you go higher up, you have less gases. That's why you have a hard time breathing. If you have less gases, you have a lower vapor pressure that you need to try to match up. So it would be less than 100 degrees, like 95, 94. The opposite. When you go below the sea level, now you have a lot of gases that are dissolving there, right? You have a lot more gases. So what does that mean? The boiling point of water is going to be greater than 100. Because you boil when the vapor pressure matches the external pressure. And the external pressure is less over here, so less you have to match. The external pressure is more over here. We talked about it, that you have more over here, so then you have a higher one to match it up. So far, so good. Okay. Now, last thing. Higher intermolecular forces. What does that mean? Higher boiling point or less boiling point? Think about this. Higher intermolecular forces. That means they're really, really attracted to each other. If you're really, really attracted to each other, you need more energy to break away. So your boiling point is going to be higher because you're attracted to each other. You're holding on tightly. I need to put in more energy in order to do that. Okay. All right. Let's do a practice problem. And then after that, I want to quickly talk about one thing about your lab that might help you out. here is our practice problem, ranking from the highest to lowest vapor pressure. Now remember, vapor pressure, all this property, boiling point, they all have to do with intermolecular forces. So before we do it, we need to figure out what type of intermolecular force they have, rank them based on the intermolecular forces, and then we'll go based on the vapor pressure. So let's figure out IMF first, okay? So figure out IMF first. Let's do this. NH3, 2 nonmetals together, you agree? 2 nonmetals together is a covalent compound. I told you guys, draw it out every time. Is it ionic? Is not ionic. 2 nonmetals together, we said you're going to count hydrogen as a nonmetal. 2 nonmetals together is a covalent compound. I want to draw the Lewis structure. Is this polar or non-polar? Is polar. And go back to our last lecture. I summarized this for you to review. So you have a covalent compound that is polar. Okay, what does that mean? That means you have dipole. You have dip. Do you agree? Okay. Does it have ionic compound? It's not ionic. It doesn't have ionic forces. Does it have dip? Yeah, because it's a covalent polar. What else does it have? It also has H bonding. Because remember, hydrogen bonding is NH, OH, or FH. And what does this one have? This one has an NH. Hydrogen bonding. So it has hydrogen bonding and it has a dip. And we said if you have dip, you also have London dispersion because everything can have a temporary dipole. So far so good. Alright, let's go to HBr. Alright, draw the HBr. Again, count hydrogen as a non-polar for all these IMF. That makes it a little bit easier. HBr. Ionic, let's say no. Hydrogen bonding, no, because it has to be HN, HO, or HF. HBr is not one of them. Covalent, yes. 2 nonmetals together. Is this polar or non-polar? It's polar because most of the electron is going to be this way. It's going to be looking the other way. Okay. Now, polar, most of the electrons are this way. So what am I? So it's going to have dipole. It's going to have dipole. So we said no ionic, no hydrogen bonding, dipole because it's covalent and polar. And then we said if you have dipole, you really have London dispersion also because everything can have a temporary dipole. You following me? Beautiful. Now, let's go to the next one. BF3. Is BF3 ionic? No. Does it have hydrogen bonding? No, it doesn't even have a hydrogen. Is it covalent? Yes. It has non-metals together. So I'm going to draw it out. When you draw it out, is it polar or non-polar? Is it non-polar geometry? So if you are non-polar, the only thing that it has is London dispersion. Beautiful. NaCl. What is NaCl? NaCl is ionic. A metal and a non-metal together. So NaCl is ionic. I can stop right there. F2. Ionic? Nope. Hydrogen bonding? Doesn't have a hydrogen. Covalent? Yes. 2 non-metals together. So I'm going to draw it out. Once it's covalent, is it polar or non-polar? Is non-polar. So if I have a non-polar covalent, the only option I have is London dispersion. So if you have covalent, if you're polar, you're dipole. If you're non-polar, you're London dispersion. Okay? And you have to, the hint is draw out the structure to figure it out. So based on this, what is my highest intermolecular forces? My highest intermolecular forces, if I had to rank the IMF, let's rank the IMF first. What's my highest intermolecular forces? My highest intermolecular forces is ionic. You agree? Okay. After that would be the hydrogen bonding. After that would be the dipole. Now I have 2 that have the same London dispersion. We said go based on the molecular weight. Go based on the total number of electrons. The heavier one, the one that has more electrons, you have a higher chance of having a temporary dipole. Which one is that? Which one is going to be? That is going to be BF3. Is going to be a bigger molecule, right? Higher molecular weight, more total number of electrons. So then this is going to be the last one. Okay. Now, we said, and this was really key, we said higher intermolecular forces means what? Means lower vapor pressure. Now, I need you to remember this. When intermolecular forces goes up, everything goes up except vapor pressure. Higher IMF, higher viscosity. Higher IMF, higher boiling point. Higher IMF, however, is lower vapor pressure, because if you have a strong intermolecular forces, you're holding on to each other pretty tightly. You don't want to go to the gas phase. So you're going to have a low vapor pressure. So I said rank them from the highest to the lowest vapor pressure. So it has to be the opposite, right? So it's going to be the opposite. So what is going to have, so which one, I'm going to rank it from the highest. So my highest vapor pressure is going to be F2. And then after that is going to be BF3 for vapor pressure. And then after that is going to be my HBr. Then it's going to be my NH3. And then it's going to be my NaCl. So this is from the highest vapor pressure to the lowest vapor pressure, because vapor pressure is the opposite of IMF. The highest IMF has the lowest vapor pressure, and the lowest IMF would have the higher vapor pressure. Okay, hopefully this was a good practice problem to kind of talk about IMF again and the physical property. So this is nice. You can look at something and you can determine what kind of physical properties it's going to have based on IMF. It's going to have a high boiling point or low boiling point. And that's pretty significant to be able to do.